In this video, I will talk about biomechanics of kettlebell swing. This figure is from Levin's et al. Paper. I was one of the co-authors in this paper, so I will use some of the results of this study for this video. One of the key features of kettlebell swing is that kettlebell is a dynamic motion enforcing almost the whole body to be involved, as opposed to other major resistance exercises targeting one part of the body, such as bench press and squat. Therefore, it can be stated that the kettlebell swing consists of the combination of closed chain and open chain exercises. So as you can see here, this figure tells us open chain part, and then this low body figure can tell us a closed chain part. Let's take a look at closed chain part of the kettlebell swing. The closed chain movement governed by the low body joint is attributable to the Romanian deadlift. The foot is fixed to the ground, and the knee, hip, ankle joint move against a linear resistance, such as ground reaction force, also known as GRF. And as you can see here, the highest GRF value occurs around the halfway of the kettlebell swing, which may be due to the effort to decelerate the downward motion of the kettlebell and also to accelerate its upward motion. So we'll talk more about the GRF values later. Here, open chain part of the kettlebell swing, the open chain movement driven by the shoulder joint during the kettlebell swing is due to an arm swing motion. So the hands holding a kettlebell are not fixed, and the shoulder and lumbar 4 and 5 joints move against the angular resistance, such as torque produced by the weight of the kettlebell. And therefore, this torque needed to be primarily focused to explain the upper body torques acting at the shoulders and lower back. Centripetal force acting toward the shoulder is also produced due to the rotation of the kettlebell. There are some mechanics to deal with in kettlebell swing. First of all, kettlebell swing can be broken down into 4 different phases based on acceleration patterns. Here, unweighing phase, and deceleration phase, acceleration phase, and unweighing phase again. And then this deceleration, acceleration occur around the halfway of the swing, as you can see here. And this deceleration, acceleration occur in both Romanian deadlift and arm swing to properly perform the kettlebell exercise. And also this deceleration, acceleration are likely to result in the maximum ground reaction force value occurring around the halfway of the kettlebell swing. However, the directions of deceleration, acceleration are different between Romanian deadlift and arm swing based on this figure. For example, the direction of deceleration, acceleration between Romanian deadlift is vertical, and the direction of deceleration and acceleration during the arm swing is clockwise and counterclockwise directions. As I mentioned earlier, a centripetal force acting toward the shoulders is also produced due to the rotation of the kettlebell. Let me explain the angular kinematics during the rotation first to understand the centripetal force. Here we have an angular kinematic condition or rotation condition. And then black dot here, the yellow dot. The yellow dot is rotating about this black dot, which means this black dot is serving as the actual rotation. And then whenever we have angular motion, the actual rotation is supposed to generate angular velocity. Here omega means angular velocity. And then rotating body is supposed to experience linear velocity. Here Vt means of tangential linear velocity, which is acting perpendicular to the direction toward the rotation center. And we can have mass here, mass of this yellow dot, and then radius as well. And in order to understand the centripetal force, we need to understand radial acceleration first. The radial acceleration means the acceleration acting toward rotation center, assuming that in this figure, shoulder joint is a rotation center. And then radial acceleration can be calculated by using either tangential velocity squared over radius, or radius times angular velocity squared. So depending on the information provided, we can use either this or this to calculate the radial acceleration. And then based on Newton's second laws of motion, F is equal to ma. Then we got here radial acceleration, and then by multiplying the mass of this kettlebell by this acceleration, then we'll be able to calculate centrifugal force acting toward the shoulder joint, assuming that again the shoulder is the axial rotation during this kettlebell swing. The kettlebell swing also generates the torques acting on the shoulder joint and lumbar 4 and 5 joint. Torque is equal to a force times momentum. Here force can be the weight of the kettlebell, and momentum can be the perpendicular distance between line of action of this force and shoulder joint and L4 and 5 joint. Although torques are supposed to increase as this kettlebell moves away from the joint due to increasing momentum for a given force, the deceleration and acceleration phases needed to be more focused, because when the kettlebell is located right here, it is unweighing phase. So the shoulder joint and lumbar 4 and 5 joints are not significantly affected by the torque produced by the kettlebell when the kettlebell is located right here. That's why you better focus more on deceleration and acceleration phase during the kettlebell. And ground reaction force is governed by the vertical acceleration and deceleration, as I mentioned earlier. And we also needed to consider moment arms from ground reaction force vector to the low body joint. And then the ground reaction force and moment arms become the greatest around the halfway of the kettlebell swing. Okay, low body net joint moment. Here moment means torque. Let's take a look at how low body net joint moment is calculated. Let me explain this free body diagram first. Here mj means a net joint moment, and rs, this means the position vector drawn from a joint center to the segmental center of mass, and ws represents this arrow. And then this means the rate of acting at the center of mass of each body segment. rgrf means the position vector drawn from a joint center to the center of pressure, and fgrf is the ground reaction force, and tz is the free or twisting moment acting at the center of pressure. And as described in this equation, the net joint moment is produced due to three components: external component, gravitational component, and inertial component. External component is coming from ground reaction force, and gravitational component is coming from the weight of the low body segment, and inertial component coming from the movement of the low body joint. Now in this formula, this part means the time derivative of local angular momentum, which is due to the rotation of the segment about its own center of mass. And then this means the time derivative of linear momentum of each body segment. So rs cross, and this means the time derivative of the remote angular momentum, which is due to the rotation of the segment about the joint. So rs cross ws means the moment produced by each segment's weight. And rgrf cross fgrf means the moment produced by the ground reaction force. According to the low body net joint moment data from Lubin et al. Study, all the low body net joint moment showed their maximum values around the halfway of the kettlebell swing. Also, the ground reaction force vector is placed anterior to the low body joint, Therefore, hip extensor, knee flexor, and ankle plantar flexor joint movements occur predominantly in the kettlebell swing. Mechanical effects of kettlebell swing on the body. First of all, you can focus only on deceleration, acceleration phases because the unwing phases do not significantly affect muscle contraction. In terms of the use of back muscles during the kettlebell swing, it is primarily due to centripetal force acting toward the shoulder joint, governed by rotational deceleration, acceleration of the kettlebell. This is because the highest angular velocity acting at the shoulder joint and the highest tangential velocity acting perpendicular to the shoulder joint occur during the acceleration and deceleration phases. For low body muscles, hip extensor muscle, which is the glute, and knee flexor muscle, which is hamstring, would be predominantly used based on hip extensor and knee flexor net joint moment result driven by vertical deceleration acceleration. Okay, this end of this video. Okay, this video covered the biomechanics of kettlebell swing.